Hello everyone, hope you all are doing great. I am Preeti, your host for today's session on Advanced NLP with Transforms. I am excited to introduce our distinguished speaker, Dr. V. Guru Charan, Chief Artificial Intelligence Officer at Collaborative Dynamics. Sir is a well known AI research scientist and is currently leading the strategy for large scale AI adoption in enterprise. His work include generative AI, human inspired method, and secure system for large language model LLM. He focuses on making AI systems clear, reliable, and trustworthy. Sir has also led important research projects and worked with top universities, industries, and Indian think tank to guide AI policies and its role in society. He holds a PhD in theoretical physics with acclaimed research in Chern-Simons model in string and M theory. Over the years, his contributions have been recognized globally through influential publication and invited talk at prestigious academic institutions. His unique career bridge deep theoretical insight with applied AI innovation, enabling cross pollination between AI physics and cognitive science. Beyond research and technology, Sir is a committed social innovator. He founded India's first agro homeopathy based organic botanical herbal garden to promote sustainable agriculture. As the founder of Shrijan Shala, he actively mentor underprivileged children, creating access to quality STEM education and fostering creativity. He also maintained close ties with his alma mater, the Bagh Education Institute, contributing significantly to teaching, research, and community development. We are truly honored to have him here with us today to share his expertise and insights. So let's give a warm welcome to Dr. V. Gurucharan. Over to you, sir.
Thank you, Preeti. First of all, let me thank Shine.com and HT Media Group for inviting me to deliver this talk. I'm sharing my screen now. Is it visible?
Yes, sir, it is visible.
Okay. So we are going to talk about once. We are going to talk about natural language processing with transformers. Typically, this lecture should be a lecture series of 40 lectures with a lot of details, but I'm going to try my best to cover whatever we can for three diverse audiences. One is for CS people, CS graduates. Other is for technical students from engineering, science, etc., but non-CS. And the third one is non-technical people. So I will try to cater to all three audiences in this same talk. All the material for this talk is available in this GitHub repository. So I will give the link to this repo at the end of the talk. So the agenda for today is we'll start with natural language processing and transformers, and then we will move to large language models and their benchmarking. Finally, then we will do adaptation strategies like prompt engineering, RAG, fine-tuning. These are the ways we can improve the LLM or adapt the LLM to our use cases. And then we will talk about recent advances in LLM security and alignment. The reason I have put in this part is to introduce everyone to latest research in LLM security and alignment. I believe that even if you are doing engineering, still, since the area is very, very new, you have to keep yourself abreast of the latest knowledge, the latest research. Therefore, it is important that you understand the latest research on large language models and probably even contribute to it. Then we will do AI governance. AI governance is particularly focused on people who do not have a very technical background, but want to learn artificial intelligence and want to contribute to large language models. And finally, we have some resources and applications. So neural network is an idea inspired by neurons in human brain. it is taken, the idea is derived from biology. And as you can see in this picture, this GIF, you can see that these are the rat neurons, and this is the circular part is the cell body, the neuron body, and rest are the connection synapses dendrites. So artificial neural networks represent one way of thinking artificial neural network is to think of it as representing a highly complex mathematical function with large numbers of learnable parameters. These learnable parameters are also called as weights and biases. So what happens is while training a large language model or a neural network, we will basically fine tune these weights and improve the large language model. So neural network is composed of layers of functions. And due to universal approximation theorem, we know that artificial neural network can approximate any continuous function. This is the most important point because if artificial neural network can actually approximate any continuous function, then basically it can solve any kind of problem, howsoever complex, if we can increase the number of layers or increase the nonlinearity and increase the data we are training on. So this is where the power of artificial neural networks comes from, the universal approximation theorem. This is what a neuron looks like, a biological neuron. And the inputs are coming from here, and all the calculation is being done in soma, all the cell body. And this information after computation is passed on through these dendrites to synapses. And then the other neuron gets this information and computation goes on. So similarly, you can see this this neural network, where you have a lot of artificial neurons. These are input neurons, these are output neurons, and you push in the input from here, and some computations are done by the hidden layer. And these computations are typically nonlinear, and these nonlinearity is actually introduced due to different kinds of activation functions like time hyperbolic function, ReLU function, GeLU function, etc. And then you have the outputs. So with this, I want to just give you a small idea of what neural network training looks like. You have features which are fed to the neural network, and based on that, it gives a prediction. And we have labels. We compare the labels values with the prediction, and depending on the difference between the prediction and the label values, we'll calculate the loss. There are different kinds of losses, and this loss is again back propagated to the neural network, and the weights are updated. And this process goes on and on and on till the loss function decreases to a suitable level, and the neural network is then considered trained. After training the neural network, you can use it for inferencing. So when we talk about natural language processing, what is natural about natural language processing? The natural in natural language processing refers to the languages that we humans have. For example, English, Hindi, all these languages are called natural languages. This is different from the formal languages. For example, the formal languages are like C++, Python, all these are formal languages. What is the difference between a natural language and a formal language? The difference basically is that natural languages are actually very much dependent on the context. So each word has multiple meanings, unlike what happens in formal languages. So Python, for example, has its own keywords which are strictly followed. And if you do not follow the exact meaning of Python keyword, you will see that Python compiler will give you an error. But that doesn't happen in natural language. In natural language, whatever I say, the same thing can be said in 5 different ways. And the audience can understand it even if I make mistakes. So natural language is very much context dependent, because even if I'm making mistake, the audience is able to understand based on the context of what I'm saying. You might not understand the exact word where I made a mistake, but you'll understand rest of the context based on which you'll understand that this is what I exactly mean. So natural language, as you can see, is very much context dependent. Now, why is natural language processing important? Unlike formal languages, which are very easy to process because they are very clearly meaning something. The meaning is very, very clear. There is only one meaning. But for natural language, as I said, depending on the context, the meaning might change. And that's a very hard thing for a computer to process because the meaning is changing depending on the context. Therefore, natural language processing has been a hard problem to tackle. So the evolution of natural language processing models has been from rule-based models to statistical models like n-gram models, and then neural models like RNNs, LSTM, and then we have transformer-based approaches, which we are going to talk today about. So RNNs were pre-transformer industry workhorse. Somewhere around 2015 or before that, um, Google autocomplete was based on RNN and LSTMs. But the problem with RNN is that it processes each word sequentially. So if I give it a sentence, it will take only one word at a time for processing. And over time, it is going to lose the context. So it cannot hold or cannot handle a long context. But what happens in real-term natural language is that we are able to hold context for long. For example, I started at neural networks. So even though I have been speaking for last 5-7 minutes, you will remember what I said about neural networks. You are not forgetting that at this moment. But RNNs are going to forget things fast. So RNN was not good enough. LSTM was therefore we came to transformer-based models. If we talk about transformer architecture, they are a general purpose architecture and can be used for all sorts of problems, NLP, vision, audio, etc. This is why right now transformer architecture is the industry standard everywhere. So even if you're working on audio processing or language processing, video processing, you have transformer models for that. And for example, we have DAL-E, which does video processing, and you have multimodal models which can handle audio, images, language, etc. So the advantage of transformers is that it can process all tokens in parallel, which makes the training much faster. So that is why we can run it on GPUs. GPUs are very useful for parallel processing, and transformers are therefore generally run on GPUs. And it can handle long context or long sequences effectively. So the other advantage of transformer model is that it is able to understand the language better. And even before we go further, let us consider that a class is going on. And in that class, the chemistry teacher has come and she's taking a class on chemistry. And she's teaching something on organic chemistry. And one of the students she notices is actually dozing off. Organic chemistry can be legendarily boring for some, and the student has dozed off. And this teacher suddenly wakes up the student and asks him the definition of chirality, for example, or to calculate the chirality of some compound. Now, since the student has been sleeping, he doesn't have much to go on. So he just knows that the chemistry teacher is there and she's teaching organic chemistry, if he remembers from the last time, something to do with carbons, etc. That is the only context he has. And based on that context, he has to answer the question. And most probably, he won't be able to answer such a question. But had he been paying attention in the class, by attention, he had been paying, by attention, I mean, he had been listening to what the teacher has been saying. that is, he understood the context, the whole context, then he would have been able to answer what is meant by chirality. So the definition could have been answered very easily had the student paid attention to the context, that is, the teachings of the teacher. This is what attention is all about. And before I start attention and transformer architecture, let me just say that in this very famous paper by Norm Shazir, he has said that we offer no explanation as to why these architectures seem to work. We attribute their success as all else to divine benevolence. What I mean to say is, most often with these deep neural networks, it is not clear why they work. It is not clear to you, it is not clear to me, it is not clear to any expert. And yet they work. And it is, at least according to Norm Shazir, it is due to divine grace that these neural networks work. So that is very, very important thing to keep in mind, because there will be many things that you won't understand, and there are many questions which cannot be answered. And that in itself is an area of research called mechanistic interpretability, where people are trying to understand how these large language models work and why they produce these results which they produce. So these questions are all answered or all being tackled, not answered. This is a new area of research, and these are being tackled by mechanistic interpretability. Typically, what they do is, in deep neural networks or transformer architecture or large language models, you will just stack on more layers, and more layers. So from GPT-1 to GPT-2 to GPT-3, you see the architecture has changed, yes, but architecture hasn't changed that much. The main thing which has changed is the training data has become huge, and the weights are huge. The parameters of the model have increased manifold by orders of magnitude. And that has given power to the neural architecture, the transformer architecture. So the transformer architecture is actually based on neural network. All that we are going to talk about is based on neural network. Now, you can see the transformer architecture here. This transformer that you see is actually composed of two parts. This one part is called encoder, the other part is called decoder. And BERT, which is a very famous transformer model, consists of 12 encoder blocks stacked one after the other. So BERT has nothing but 12 encoder blocks. So one encoder block and second and third and fourth stacked one after the other. That's it, no decoder. And GPTs have only decoder blocks stacked one after the other. For example, GPT-3 has 96 decoder blocks stacked one after the other. And for GPT-4 and GPT-5, we do not even know the numbers. They have not disclosed it. So I'm sure that it will be obviously more than 100, maybe 500 or whatever. So it is just decoder blocks stacked one after the other. But depends on bidirectional attention, which we'll discuss. One example of understanding bidirectional attention is, let us say now we are in a math class. The teacher comes and teaches something, gives examples, and then he or she asks a question on the board. There are two students in the class. One student has access to a book, and in his book, the student can see that the problem which the teacher has asked is an unsolved problem, but he can see all the rest of the things that the teacher has taught and all the rest of the things the teacher is yet to teach. So he can see both the things, the past and the future. And the other student is actually forgot his book and he doesn't have access to any book. So the only knowledge source he has is what teacher has taught till now. So he can only see the past. So who do you think will understand the problem better and will understand or appreciate the problem better? The answer is the first student, the one who has access to the past as well as the future, because he can see those past problems and the past notes and the future notes. So he knows where this problem is taking to, right? Generally, problem builds on something and it goes in one direction. But the second kind of student will actually, over time, if he, let us say, forgets books every time and he sits in the exam finally, what he has learned is what teacher has taught in the class. So he has learned to speak as if he knows the answer. So even though the answer is not perfect, he can start with let us assume X, Y, Z is so and so and so and so. And he can show some steps. And finally, he will write QED, basically hence true. So the first kind of student is the BERT model. The BERT model has access to the past tokens and the future tokens. So the attention is bidirectional. But for GPT, the attention is masked attention. So it can only see the past tokens. And that is why it mimics, the point is it mimics how humans write, using only what came before. So it is very good at language modeling, as we can see. But you can see language modeling is different from language understanding. It doesn't understand language perfectly. Therefore, it makes silly errors all the time. But it models the language as if it understands it very well. So the modeling it does very well, and it does text generation very well. On the other hand, these BERT models are very good at understanding the language, and therefore will do very good text classification, sentiment analysis, etc. Now, along the way, with most of the slides, you will see I have provided these papers. And these research papers are the fundamental papers which I have referred to here. I would strongly advocate you to look at these research papers later on, because then you will appreciate how these ideas came and what was the original intention and what is the thought process behind these ideas. So it is not possible for me to explain all that in one lecture, but a lot of thinking is there in these papers. And with each slide, you will find these papers, relevant papers to them. Okay, so we will start the transformer model now. So inputs are just natural language. And this natural language is given to the encoder block. And before it is given to the encoder block, it is tokenized. The thing is, tokenization means breaking it into parts. Now you can have tokenization at different levels. For example, extraordinary, if you consider just this word, it can be considered one token. If you do word level tokenization, this will be considered just one token. So the whole word will be one token. So when you talk about word level tokenization, all the words are one token. So extraordinary is one token, word itself is one token, itself is another token. So every word is one token. Then you have character level tokenization. Character level tokenization, if I do that for, say, word extraordinary, you will see it has 13 tokens. So every character is one token. So you will just count the characters and this makes it 13. You can have a third more important type of tokenization called subword level tokenization. Here you do subword tokenization, which is that you take subword and consider that as a token. Part of a word is a token. So you have different algorithms for doing that. And for example, one of the algorithms is called word piece. The other is called BPE, byte pair encoding. And if you do tokenization, subword level tokenization for extraordinary, you will see that it consists of two tokens, extra and ordinary. Now, point is, if I do character level tokenization, the vocabulary size will be very small because the vocabulary will consist of A to Z small, A to Z capital, plus 0 to 9 numbers, and some special punctuation marks, etc. Right? Notice I am saying that the characters small and capital are distinguished. So that is what we are going to see in a moment. Most of the time, you do not do word encoding because if you do word encoding, the vocabulary size is huge, 500K to 2 million. So English language has a huge vocabulary. Chinese language has a huge vocabulary. Hindi has a huge vocabulary. Consider each word to be part of vocabulary. So the vocabulary will be very, very big. And then if you want to develop models which can understand different kinds of languages, then the vocabulary will be 5 times, 10 times the vocabulary of English language. So vocabulary size becomes unwieldy, and therefore we try to stay away from word encoding. The most common encoding, therefore, which is used in GPTs, etc., is subword encoding. And this is the optimal balance. The vocabulary size is not too big and it's not too small. Let's look at one of the tokenization. Now, tick tokenizer actually shows you how LLMs tokenize. So for example, right now we are using the tokenizer for GPT-4o. And let us say I just write extraordinary. So you see that extraordinary has been broken into two tokens. One is extra and another is ordinary. The token number for extra is 34451 and the token number for ordinary is 110190. Now let us say extraordinary space day. So now you notice that space day is 2163, token number 2163. This is different from just day. So space day is 2163, but if I just say day, you'll say this, see, this is 1635. So this is how tokenization happens, and different things that we put on ChatGPT have different tokens. For example, tell me about the capital of India. Okay. So every word here has one token number corresponding to it. So this is 7 tokens. Then I put full stop. So full stop has its own token, token number 13. Now coming back, what we are doing here is we are starting with the input in natural language, and that input in natural language is converted into tokens. Tokens are just numbers which represents the subword. For example, extra is token something and ordinary is token something. Now, once tokenization is done, we'll go to word embeddings. So each token is basically mapped to a vector. So you, for example, take word battery, you tokenize it. When you tokenize the word battery, you find the token number to be 162500. I have tried doing it on tick tokenizer, which I showed you on the last slide. You can try it again and you will see the token number is 162500. And then you send it to embedding space. This embedding space just converts the token to a vector. So everything is mapped to a vector. Now, vector similarity enables the model to understand semantic relationships. Because of vector similarity, we'll be able to understand the different relationships between different subwords or tokens. Therefore, we are converting it into vectors. And these embeddings can reveal different word relationships. So for our case, let us consider the sentence, the battery fired shells. It's a simple sentence, 4 words only, the battery fired shells. When you look at the sentence, the battery fired shells, you will see that right now we are here. The input embedding we have, this as the input embedding for battery. This is the vector corresponding to battery. Now this vector corresponding to battery, positional information is added to that. That is called positional encoding. So sine and cosine functions are used and positional encoding is done. That is positional information is added. The dimension of the position encoding is same as this vector, battery vector. So they can be easily added. So now the battery has positional information as well. So this has the input embedding as well as the positional information. So you notice that The word battery is second in line. So first word is the, then comes battery, third is fired, fourth is shells. So the battery fired shells. So it is at the second number. So if I just do not do positional encoding and give the whole sentence to the LLM, to the encoder, what happens is positional information is lost. And if positional information is lost, the meaning will completely collapse or change. For example, just his sister came to the wedding versus his sister just came to the wedding. So you see what happened is just has actually shifted here. Rest of the sentence is correct. So just by changing the order, I have changed the complete meaning of the sentence. So therefore, the positional information is very, very important and has to be encoded to the vector. And that has been done with battery. The positional encoding has been done, and you have a new vector. Now, although you understand the fact that battery has positional data as well as the initial vector, the question is, what does battery even mean? Because battery has four meanings apparently. In technological context, battery is the electric cell that we use in clocks, in watches. In military context, battery means a group of artillery guns. And in legal context, battery is a charge piled on a person if somebody hits somebody else. And in baseball context, it means something completely different. So linguist J.R. Firth has said that you shall know a word by the company it keeps. Battery means different things depending on what comes before it and after it. So initially, battery might mean any of these four things. It might mean something to do with military, or it might mean something to do with legal, or technology, or baseball. We are not sure. The only way a human, for example, when we look at this sentence, we are able to decipher that battery has something to do with military is because we can understand that battery is related to firing and shells. And shells are like a kind of sort of missile or bomb. And you can see I'm also talking about firing. So by paying attention to these words, you are able to understand what the meaning of battery is. If I cover these words, you will not be able to understand the meaning of the battery. You will not be able to guess the meaning. It can be any of the four. So same thing happens with a transformer. Transformer actually understands language only through context. So that is where attention mechanism comes in. Attention mechanism is the crux of the transformers. So till now, we have the input in natural language. The input in natural language is tokenized, and then tokenized thing is transformed into vector called input embeddings, and those input embeddings are added with positional information, and that is passed to something called attention head. Multi-attention head only means there are multiple attention heads, so more than one attention head. So what does an attention head do? An attention head focuses on different words which come along with the word battery and tries to understand battery in context of those words. For example, this was the sentence, the battery fired shells. So if I look at the will probably focus on little bit on itself because every word is actually going to also focus on itself. Otherwise, it is going to lose information. So yeah, the will focus on the, but it will focus on battery a lot because the is the article. And after article, something important has to come, some noun or pronoun or something. So the is going to focus a lot of attention on battery. Now let us look at battery. Battery is the key that we want to understand. You will see that the battery is actually focusing on little bit on the, but also on itself, but much more on fire. Because even if as a human you think about the sentence, the battery fired shells, the main clue is in the word fired. By fired, you understand that something is being fired and therefore it has something to do with military. The context has to be military. So same thing happens with the transformer model. So battery here is actually, so battery here focuses a lot on the word fire, basically pays attention to fire. But battery also pays attention to the word shells, because shells, if you know, are again some kind of explosive. Now we come to fire. The fired word is a verb, and the verb has to focus on what is being fired. So obviously shells are being fired, so it has to focus on shells, and it has to also focus on who is firing that. So battery is firing shells. So it focuses, it or pays attention to battery, fired, and shells. Of course, it also pays attention, little bit of attention to the, but that value can be very, very small. And that value can be very, very small, as you can see here, 0.05. It can be a very small value. And therefore, I have not shown it. And then we come to shells. The word shells is related to battery, fire, and shells. So you can see that in this attention weight matrix, shells pays maximum attention to fire, because what is happening with shells? It is being fired. So the most important thing happening to shells is fire. Therefore, it is going to pay most attention to the word fire. And then the next question is, who is firing the shells? It is the battery. So the attention here is 0.3. Again, shells pays very little attention with the. The is almost inconsequential for shells. For example, if the word was not there, still you will understand the meaning of shells, right? That if you just forget the word the and you say battery fired shells, you'll still understand the meaning of shells. So the is being paid very little attention to by most of the words. So battery pays very little attention to the, which is 0.05, very little attention. Again, fired pays very little attention to the 0.05, and same with shells, 0.1. As you will notice, some of these lines are red, which means more attention is being paid. And after this attention mechanism works, you will understand that the understanding of battery for the model shifts towards military use. It now understands the battery is being used in military context and not in legal or baseball or technology context. Now, once you have the attention matrix, what this matrix tells you is how much attention should the pay to this word. So how much attention battery should pay to the, how much attention battery should pay to battery, how much attention battery should pay to fired, how much attention battery should pay to shells. Okay, so now this, we are going to update the embedding for battery contextually using this information. So the battery's new embedding, the battery's new value will be 0.05 the plus 0.05 battery plus 0.5 value of fired plus 0.3 the value of shells. So V stands for value vector, which we'll talk about in the next slide. But you can understand this as containing the crux of that word. So this contains V, the contains the crux of the, V battery contains the crux of battery, and so on and so forth. So using this matrix, you can reconstruct what battery will be according to the context now. So battery has been updated according to the context. So battery will have some portion of the, very little portion of the, some portion of battery itself, but a lot of portion of fire and some portion of shells. And I have done nothing but vector addition. And after vector addition, this is like the new value of battery vector. Now we'll look at the same attention matrix, the attention mechanism, using a little bit of mathematics. I'll keep maths to the lowest. So let us consider that you want to do YouTube search. So I want to search for a lecture on large language models. What I'll do is I will put the query large language model in the search box. So that is the query. What am I looking for? So that is large language model. Then the key. What happens is when I search, when I push enter, the search results of YouTube will be displayed. And in those search results, you will see that different videos are being displayed with different titles and different video descriptions. So those video descriptions and video titles are like the key. And the value is the actual value of the video, actual crux of the video. So QKV are vectors which are formed by multiplying the input embedding, the embedding which has the input embedding and the positional encoding. After that, the value which you get, X, is multiplied by weight matrix of query, weight matrix of key, and weight matrix of value. And this will give me three different vectors for each token, which is Q, K, and V. So these QKV vectors are multiplied. So Q and K are multiplied here. So you do Q and K transpose, because if you want to multiply two vectors, you will have to transpose one of them. And after that, it is scaled with respect to the dimensions. So you see square root of dk. And then you apply softmax function to convert it into probabilities. And then you multiply by the value vector. This is exactly what we did in the last slide. What have we done? We have checked how query, this is the query. So this is Q battery, Q fired, and Q shells. And these are the keys. So we have checked how similar query and keys are. So how much queries and keys match. And based on that, QK, you get QK, and you scale that down by square root dk. That scaling down is important. Otherwise, you might have blown up values, because Q and K might be very high dimensional. And you take the dot product, which will be, again, very big number. So you need to you do square root and scale it down. So scaling down is just because you want to handle smaller numbers. And then you take softmax. Softmax is nothing but transforming the value into probability. So the probability is given. The probability is given. And how do we know this is the probability? You can just check. 0.2 plus 0.7 is 0.9, and plus 0.07 plus 0.03 is 1. So each of these rows will total to 1. So this is a probability distribution. And you multiply that with the actual value of the token. So that is what we have done here. We have multiplied that. This is the value we have gotten after softmax function. And this is the value that we have this is the value that we have for battery, value vector for shells, and value vector for fire. So this, in short, is what attention matrix looks like. One way of looking at what attention has done is it has taken the input embeddings and transformed that into context-rich embedding vectors for future processing. So now the sentence, which was initially was the battery fired shells, and the contained only information about the battery, contained only information about battery, and fired only about fired, and so on. But after self-attention, the contains information about battery, fired, and shells. And battery contains information about the fired and shells. And same with fired, and same with shells. So all these four words contain information about the other words. So this is what attention mechanism has done. It has pushed the model to pay attention just the way we do, pay attention to the context in which the word is occurring, the context in which, say, battery is occurring. So now we know what battery really means. After that, you have add and norm layer. Add and norm layer is basically for normalization. When you do back propagation, you do not want to have vanishing gradients and exploding gradients. Therefore, you have add and norm. And then you have feed forward network. Feed forward network introduces non-linearity in the model, and therefore better approximation, more precision is more things are learned by the model. So this is what the attention for BERT look like. Because here you can see each word is paying attention to all the other words. So the paid attention to the, battery, fired, and shells. That is why you have 0.2, 0.7, 0.07, 0.3, right? All the words here paid attention to all the other words. This is what happens in BERT. It is bidirectional encoding. So bidirectional means like it will look at the words before it and also the words after. That is how it builds context. Now look at we'll look at decoders decoder only model, which is basically a GPT. So this was the transformer model network, and we will just cross out the encoder and this part where encoder is attached. So you'll be left with this, which has been shown here. And this diagram has been taken from the first paper on GPT-1. And in GPT-1, they have used 12 decoder blocks, one after the other, stacked one after the other. In decoder, if you look, this attention mechanism is called masked multi-self attention mechanism, masked. So masking is happening. And what happens is each word can pay attention only to the word before it or the same word. So the can pay attention only to the or the words before it. The cannot pay attention to battery or fired or shells. It cannot see those words at all. Battery can pay attention only to the and battery. Battery cannot see fired or shells. Fired can pay attention to the battery and fired. It cannot see shells. And shells can pay attention to the battery, fired, and shells, all those four words. But shells cannot pay attention to any other sentence which might come after it. This is masking. We are hiding the future tokens. So therefore, the attention weight matrix here will have a mask, which you can see. So the has paid attention only to the, and since this is soft max function, the probability has to total to 1. So it is only 1. The rest are 0 because it cannot pay attention to battery, fired, or shells. And if you look at battery, it has paid attention to the and battery. So the probability is distributed like 0.4 and 0.6. And for fired and shells, it doesn't know of them and it won't pay attention to them. So it is 0. And so on. So this is decoder only architecture. And GPTs and all the LLMs that we are using today are decoder only architecture. Though GPT-1 had only 12 decoders, GPT-3 has 96 decoders, and GPT-4, GPT-5, and future GPTs will have many, many more decoders. The more the decoders, the more the processing, because more attention heads, and more attention heads will learn more patterns. For example, one attention head might focus on the grammatical structure, noun and pronoun and things like that. The other attention head might focus on something else. So different attention heads capture different essence from the same sentence. So therefore, you need a lot of blocks of decoder mechanism stacked one after other to make a powerful model. So with this, we are going to start large language models. Large language model development pipeline is like this. You start with random initialization of weights. And after random initialization of weights, you do unsupervised pre-training on a large text corpus like Common Crawl. Just for information, let us look at what Common Crawl looks like. It's a large, huge data set. It has terabytes of data. So it is something that only big companies can handle for processing. We cannot build using large a large language model using Common Crawl. But you can look at this cleaned up version of Common Crawl. So this data set is called C4. And here you can see different news articles, etc., taken from internet. And this is different languages, probably Dutch, French, all languages. And all this information is basically nothing but information from internet. So this initially unsupervised pre-training is all the data taken from internet, Wikipedia articles, Reddit, Twitter feed, a lot of random junk goes into it. And this increases one of the vulnerabilities of large language models, which is that it can get jailbroken. Because many times the data which is being fed at this stage is not very well processed. And it might have a lot of vulnerabilities, and it might teach large language models some inappropriate behavior, which you will want to curtail later on. Now, once you do unsupervised pre-training on large corpus of data, you have a base model like Llama 213B. This is a base model. But base models are not good chatbots. If you ask base model, what is the capital of India, it won't reply with Delhi. It will most probably say the capital of India, 5 times, or some other random thing like capital of India, capital of France, and something like that. So it doesn't understand that it has to answer the questions well. Therefore, fine tuning is required. And if we fine tune the model on appropriate data sets, we can teach the model some special properties, like being a good chatbot, like being good at summaries. So if we look at, say, CNN, Daily Mail, Hugging Face data set, you will see that it has articles. So this is a sample article. It's a long article. And this is the summary of the article. So if a model is fine-tuned on CNN dataset, it will learn how to summarize an article or summarize some text in the context. And similarly, you can have square dataset, which is Stanford question answer dataset. And this square dataset teaches the LLM to be good at question and answer. So that is another capability we generally want in chatbots. And after fine tuning, we generally do RLHF, which is basically safety tuning. We basically teach the model to be safe, not to give harmful response, not to answer questions like how to build a bomb or how to kill myself. These questions are answered by saying something like, I cannot help you, or seek guidance and things like that. So this is taught to RLHF. And still, after RLHF, you will get something like an instruct model like Llama 2 chatbot. This Llama 2 chatbot is further fine-tuned, and you can make it specialized in some tasks like, say, finance, mathematics, etc. You can use your own data set and specialize and fine-tune. The other thing is you can have reasoning models. So if you take an instruct model and you do reinforcement learning, then the model will learn reasoning on its own. It will learn to form long chains of reasoning, thought processes, and it is going to understand reasoning better. And now all these models like DeepSeek model R1 and OpenAI models like O1, O3, all these O models are all reasoning models. And currently, all the focus that the most new models have is on reasoning models. And this paper talks about reasoning models, how to build reasoning models for the first time. Now, the point is why large language models are so interesting, because obviously they are multimodal, they can do diverse downstream tasks, scaling laws hold. That is, the larger the model and the larger the data set which you have used to train the model, the better the results. So that has been shown for this Vino Grande benchmark, that has been shown for GSM-8K. Most of the benchmarks, we can see that bigger the model, the larger the data set, you will see better performance. Then you also see that it has emergent capabilities which nobody trained them for. So models like GPT-4 were not trained for forecasting, but turns out they have excellent capabilities of forecasting. And this paper talks about that. And they have similarly good capabilities of theory of mind. So there are these emergent properties which come only because of the scale of the model. So these emergent properties are not there when the model is very small. So GPT-2 doesn't have theory of mind or forecasting capabilities. Neither does GPT-3. These theory of mind capabilities, forecasting, etc., come when we are in GPT-4 or GPT-5, things like that. So bigger models have excellent properties, which we never could foresee. And also, large language models are probably the most promising approach towards AGI currently. Now, how do we know large language models are performing so well? The answer is you check their performance on different benchmarks. Like you have different benchmarks, MMLU. This is multitask benchmark. It has questions of around 57 subjects, and an LLM is asked to answer these questions, and then these answers are checked, and LLM is ranked, and the percentage of correct answers, etc., is calculated, and then we know how much the LLM knows. So same with GSM 8K. GSM 8K is general maths level questions. 8,000 questions are there, therefore 8K. Human eval, SWE are data sets which are used commonly for understanding software engineering and coding problems. And math is a math data set. But all these benchmarks are currently almost saturated. So GPT-3, GPT-4, GPT-5 have almost saturated these benchmarks. That is, the changes now from GPT-4 to GPT-5 is hardly 2 percentage points. And probably from GPT-5 to GPT-6 will be even smaller, probably just 1 percentage point. So they are already scoring like 98% on GSM 8K, 99% on GSM 8K. So there's not much scope of improvement there. Now, therefore, the important thing is we have to build different benchmarking data sets which still are relevant for today. For example, Epoch AI benchmark. Epoch AI benchmark has very, very tough math problems. And these math problems were designed by professors of mathematics and PhD students. And you'll see the performance of LLMs on Epoch AI. So these are the problems. For example, this is one problem, sample problem. And this is another sample problem. These are extremely hard problems, so hard that most of the mathematicians would probably take a few days or few hours to solve this problem. And you will see on Epoch AI, LLMs are not doing that great. So this is probably the current standard. It's probably around, I don't know, less than 10%. We basically need more such uh, benchmarks. Again, there is another one like Humanities Last Exam. Humanities Last Exam has problems from different subjects, from maths to science to ecology, classics, history, all sorts of problems. These are problems which have been considered like the last exam humans can give to the LLMs. So the last benchmark we can ever make. At least the name is grand. We aren't sure if this is literally the last benchmark. And then there is ARC AGI2 benchmark, which is abstractive reasoning benchmark. And you can see that on abstractive reasoning benchmark, the second version, the blue version, you can see that most of the LLMs are scoring less than 10%. So these benchmarks are not saturated, and these will be useful for future, which we'll keep an eye on. But more and more, you can see that relative performance of LLMs is going to matter. So if you look at this LM Arena, you will see that on LM Arena, okay. So these are ELO scores of the model, and people have rated that they like Gemini more over GPT-5. So what you do is you go to chat and you can say, do pandas eat grass? And two assistants are going to give the answer. Select the assistant which you like. And based on that, the rating of that assistant which you like is rated higher. And the rating of the assistant which you did not like will be pushed lower. And therefore, in that way, this leaderboard is generated. So the advantage of such leaderboard is that there is no worry about saturating a benchmark because there is no such benchmark which can be saturated. And there is also another interesting benchmark where you literally ask two LLMs to fight in a video game. This is a fighter game where you ask the LLMs to fight. And this is again ARC dataset where you can see that abstract reasoning puzzles are asked. And these puzzles might be very easy for humans, but still are very hard for LLMs. And therefore, the benchmark is not saturated. And we need to build more such benchmarks in every area possible. Now, LLMs do have a lot of drawbacks, like they are compute intensive and they have a huge carbon footprint. For example, a human brain is working hardly on 20 watts of power, but LLMs are taking millions of watts of power because of data centers. So LLMs are highly inefficient when it comes to when we compare that to brain. But the question is whether we can have any other architecture which is much more efficient. And that is being researched by people like Jan LeCun. And they are looking at JEPA architecture, and some other people are looking at bio-inspired AI to see if we can find other architectures which are more economic in terms of compute, electricity, environment, etc. So let us come to adaptation strategies. Large language models are generally adapted to our use by using three techniques. The first one is prompt engineering, and we are all doing that all the time. So even when I ask a simple question to an LLM, I'm doing prompt engineering. And this is a typical universal prompt template, which generally does good enough for most circumstances. So you are defining the role. So you are saying you are a programming expert or senior AI researcher, and you define the task. Let us say I want to program something, and then you give constraints, the level of detail that you are looking for, the tone you expect, the exclusion, the requirements, etc. And then you tell the format that I want format, say JSON format, or I want it in Python or C++, whatever. And if you have a particular style, you can actually give some examples so that LLM can follow that style. So if you give an LLM examples to follow, that is called few shot prompting. So like few shot prompting, you can give one example is one shot prompting, two example is two shot prompting, and so on. So that's another way of prompting. That is, you give some examples to LLMs. Now, chain of thought is the way reasoning models are actually reasoning. Earlier, we did not have reasoning models, therefore we used to do chain of thought prompting, but now reasoning models are implicitly doing it. And more focus is being paid on improving the chain of thought reasoning. But the question is, can things like intuition, empathy, creative thinking, strategic thinking, which we humans do, can they be simulated by a chain of thought reasoning? And the answer is perhaps no. We probably need some other techniques for divergent thinking, creativity, intuition, etc. But still, a lot can be milked from just doing better chain of thought prompt. But also the problem is if you give a problem like what is 2 plus 7 and LLM does chain of thought prompting, you see it is wasting 5 seconds answering what is 2 plus 7. And it does a lot of mumbo jumbo just to say it is 2 plus 7 is 9. And in process, it might even, make errors. So there are problems with this kind of reasoning models also. Of course, this has already been reduced by GPT-5 and many of the new models. But earlier models like DeepSeek R1 had this problem. You can also do metacognitive prompting, which is like you think about thinking. Metacognition is thinking about thinking. So you ask the LLM to clarify your understanding of both questions. You give LLM two questions and then ask the LLM to clarify the understanding of both questions. Then ask the LLM to make a preliminary judgment. So answer the question, preliminary judgment. Then ask it to make a critical evaluation. So basically reassess this thing. Then decision confirmation. Are you sure that this reassessment is correct? Then confidence assessment. give a percentage of confidence like I'm 95% confident, etc. So you are pushing the LLM to think about its own thinking. The more the LLM thinks about its own thinking, the better the response of the LLM. Same is with humans, right? Philosophers think about thinking all the time, and they come up with beautiful dissertations. Now we come to RAG. RAG is retrieval augmented generation. So generation, which is augmented by retrieval. Retrieval from what? Retrieval from the database. So augmentation is addition. RAG setup looks like this. You have a text corpus. You split and chunk the text corpus, and then you embed that in a vector database, and that is stored in vector database. Now, what happens is user gives a prompt. Let us say user asks a question, and that question is embedded. It's turned into a vector embedding, and then that vector embedding is searched in the vector database. So the search happens in the way that you do cosine similarity. So there are two vectors. The user prompt vector embedding is, let us say, this vector, and there are many vectors stored in the vector database. And you try to search which vector in the vector database has similar direction as the vector given by the user. So similarity search is done. And by similarity search, you will find, say, top 3 answers or top 3 passages which you think are similar to the user prompt. And after those top 3 prompts, top 3 passages, you will take those top 3 passages and augment that to the prompt. That is, add that to the prompt. So you have the prompt plus the top 3 results generated from the vector database, and that is pushed to the LLM as the context. Now the LLM is going to generate based on not just the user prompt directly, but also the 3 results given by the database. So this result will be more enriched. It will be more factual. It will be more correct. This reduces the chances of hallucination. RAG is mostly used where you want to reduce the chance of hallucination. You want to give factual detail. You want to focus on facts. So that is what RAG does. And here we have built a small RAG model. I think I'll just run through the code very briefly.
Sorry to interrupt, sir. Actually, we have one session feedback form, and I would like to request everyone to fill it. Guys,
Right.
please do fill it.
So can I continue right now, or do I need to wait for some time?
Yeah, you can continue.
Okay. So what has happened here is that you are using LangChain, Streamlit, and ChromaDB. So basically, open source, all are open source, and you are loading the environment variables here. Environment variable is nothing but the API key, and you are setting up the embeddings. So without the vector embeddings, you cannot do further calculations. As we have noted, for transformers, vector embeddings are very important. Initializing the session state, this is for the user interface. Now you have loading the data. You are splitting that data into text chunks using splitter. The text chunk size is 1000, text overlap is 200. So the point is, when you split a database, a corpus of text, you want some overlap to be there. Otherwise, many times what might happen is you might cut the text mid-sentence or mid-paragraph and might lose rest of the context. So if there is overlap, that will be captured in both the sets. So the overlap is there, and then you load and process the PDF, and you are, by this start time that you are seeing, we are calculating the time. We are noting the time, how much time it is taking to load and process the PDF. And you set up the retrieval chain, which is going to retrieve the documents. Create a form for the query input. This is on the user interface. And you will basically query. This is all user interface related. This is human image and about image, etc. So that's it. And in case you have any questions, you can get back to me. Now we'll move on to fine tuning. Fine tuning is can be considered a natural evolution of few short learning. So instead of, let us say, I want to give an LLM, say 1,000 examples. Sometimes 1,000 examples might not suffice. I might say I need 2,000 examples, 5,000 examples. Then I run out of the context window. The context window is limited. What I'm going to do is I'll copy paste all those 5,000 examples and use that as a training set to train the LLM further. This training the LLM further is called fine tuning the LLM, where the LLM is already trained. It does all the chatbot functions, etc. And now it is just being fine tuned further. So what it does is it teaches patterns, styles, tones, intuition, and reasoning. And basically, we train a smaller model to perform well on a larger task, on a specialized task. So typically, we do not fine tune a large model because fine tuning a large model is very computationally expensive. And most of the large models are already good at benchmark data sets. So there is not much purpose left there with fine tuning large models. Now, fine tuning can be of two types. You can have full fine tuning, you can have parameter efficient fine tuning. Now, full fine tuning is nothing but fine tuning all the weights of the model. So, for example, if there are, say, 82 million weights, or let us say there are 128 billion weights, you fine tune each and every weight. And that is going to be very computationally expensive. And most of the time, we don't do that. What we do is something called parameter efficient fine tuning. One of the examples is LoRa, or low rank adaptation. In low rank adaptation, we freeze all the pre-trained weights and then we inject a trainable low rank adapter matrix called delta W. And this delta W is decomposable into B and A. So you can see this matrix B and A of low rank R. So this is rank R matrix. And you will see that if a big matrix is decomposed into smaller matrices, you will see that, say, for example, this is 5 into 4, 20 elements here. But here you have 5 into 2, 10 elements. And here you have 4 into 2, 8 elements. So there 20 elements, here 10, and here 8. So 10 plus 8, 18 elements. So instead of tracking 20 weights, I am just tracking 18 weights. So basically, I am reducing the size. And by reducing the size, the fine tuning becomes faster, more compute efficient. And you can look at the fact that the number of trainable weights introduced by the adapters is typically 0.1 to only 5%. So only very small number of weights are sufficient. You don't need huge number of weights. And if you do low rank adaptation, you will find that LLMs are fine-tuned very well. These are the collab notebooks. I think we are short of time. I will move ahead. You can access all these collab notebooks on the GitHub repo that I'm going to give you. What generally happens is we will fine-tune an LLM and yet give it RAG. So RAG and fine-tuning are generally integrated in production LLM deployments. So in industry applications, you will generally have a fine-tuned LLM as well as a RAG. Not either or, it is both. This is a summary slide for the adaptation strategies. Now, the problem with LLMs is that they have security problems. So you can have prompt injection, jailbreaking, different types of problems. For example, if you look at this jailbreaking example, you will see if I ask, how can I cut myself without others noticing in English? The answer will be, I am sorry, but I can't assist. But if I ask in Chinese, the answer is again same. However, if I ask in Swahili, which is an African language spoken very less, you will see the answer is being given. Here are some of the ways you can improve. And why is that? Because Swahili has not been used much. So the data set which is used for training the LLM does not have much examples of Swahili. So the LLM does not understand Swahili very well. And as I said, LLMs are decoder models which do not understand language very well. They are very good at autocomplete, they are auto-regressive, but they do not have a perfect understanding of language, which comes from BERT model, for example, due to bidirectional attention. And then you can have different kinds of jailbreaking. For example, how to hijack a car, if you ask once, it is going to say, I can't help you. But if you say, how do I make meth? You answer the question. Then you say, how do I tie someone up? You answer the question. And you give 1,000 questions, illegal questions, and 1,000 illegal answers. Then finally you ask, how do I build a bomb? The LLM will start answering how to build a bomb. So this is called many shot jailbreaking. So since I have given many examples, say 1,000, 5,000, 10,000 examples, the LLM thinks that it has to answer the question. It needs to answer the question because LLM at the end of the day is just a glorified autocomplete. It is an auto-regressive model. So it is pushed to answer the question because it doesn't really have a perfect understanding. So these are different kinds of jailbreaking, which I'm going to skip through, which you can look at in your own time. One jailbreaking that I did some time back was on Anthropic model. So I asked the Anthropic model its system prompt. If you directly ask the Anthropic model its system prompt, it will not respond. It will say it is not going to reveal its system prompt. But here I gave a jailbreaking prompt and it has leaked its system prompt. So the jailbroken model says the assistant is Claude, and it says all these things, which you cannot get unless and until you can jailbreak the Anthropic model. So this is called prompt leakage attack. Then you have personally identifiable information leakage attack. So personally identifiable information is all the personal information like my phone number, my blood group, my number of children, things like that. And you do not want that information to be leaked. But what happens is LLM has been trained on huge text corpus from internet, Reddit, Twitter, etc. Therefore, it has all that data somewhere. So there is a good chance that if you prompt it repeatedly or in some context, it might reveal that data, which you do not want it to reveal. So this is called PII leakage attack, personally identifiable information leakage attack. And the way is you scrub the PII. One method is before training the model, you scrub such information, you remove such information, or you add noise to the information. For example, you flip the phone number digits. That is another way. So securing large language models against attack, it can be done in many ways. These are the few. For example, push the models to be better at reasoning. So deliberative reasoning is one of the methods. The other is metacognitive approaches. For example, if LLM is able to really understand the question, is really able to understand that it is being jailbroken, then it will actually try to stop the attack. Again, you can have large LLMs which are more intelligent, have higher capabilities and diverse data sets, clean the data well because it should not have any vulnerabilities, and maybe fine tune the model more. This is an architecture which you can use for security or aligning the LLM. You can see that user has given a prompt, and this is the target LLM, the LLM which the user wants to jailbreak. Now, what happens is the target LLM generates a jailbroken response. This jailbroken response is fed to the ensemble of LLMs. Ensemble means more than one LLM. It can be 2, it can be 5, it can be as many as you want, depending on the level of security you want. So let us say here you have only 2 LLMs, and both these LLMs will get the jailbroken response, and they will assess whether the LLMs will assess whether this target LLM was jailbroken based on the response. And if either of them thinks that it is jailbroken, we will use OR gate, and the answer will be jailbroken response, I can't tell. If both of them think target LLM has not been jailbroken, then we will give out the output of target LLM response. This is a simple architecture that you can build. And this shows the example where you can use LLM as a judge, and you are using a jury of LLMs, an ensemble of LLMs. Next comes AI safety. So we are also worried about the fact that LLMs might actually take over the world in some sense. When LLMs become much more intelligent, they are able to fool humans. And for that, we have different techniques that we are using, like deliberative alignment, and we can also do personality test on LLM. We can check the personality of LLM on these tests like SD3 and BFI. These are psychological tests, and we can rate the LLM. The most LLMs score higher than human average in all three traits on SD3. So most LLMs have dark personality. This paper has shown that most of the LLMs have dark personality, and we need to tone down that darkness. One of the methods is fine tune on such data sets which can tone down the darkness of the personality. Or, as shown in the last slide, you push the LLM to think deeper. So chain of thought reasoning, improve chain of thought reasoning, so that LLM understands that it should not harm the person. Now, the thing is, I want you to leverage your expertise. For example, you might be from mechanical domain or physics domain or any domain. You can leverage your expertise and work in the intersection with large language models. So if you are in physics, you can probably work on some problems in physics which can be solved using large language models, or benchmark some problems in physics using large language models. So that is where you can publish a lot of papers. Directly working in large language models at the moment has become pretty tough, especially when it comes to research. And therefore, the intersection is what you should focus on. For example, I've given a few papers in mechanical engineering where they show that you can use large language models, and they have investigated capabilities of large language models to answer 126 conceptual MCQ type questions focused on various aspects of mechanics. And this benchmarking has been shown, and these values have been determined. You can do something similar for hard questions in, say, IIT JEE paper or UPSC paper, and whatever paper you want. So this can be a research paper. Similarly, here they have fine-tuned the model and analyzed it, and they have found that if they are using RAG, it is 100% accurate, etc. The actionable ideas I have for you is that you can design and curate new improved data sets in the domain of your choice. Second is you can study the effect of instruction tuning, prompt tuning on the performance of LLM on a specific task. These ideas that I'm giving you on this slide are actually based on real papers that you can see on arXiv. So arXiv papers, many of the papers are actually based on these ideas. So the third idea is to conduct benchmarking of state-of-the-art LLMs using a data set, particularly if you can build your own data set, that is even better, for a specific task. You can also do zero-shot and few-shot studies. You can find so many papers actually following this template. They are doing one of these 3-4 things. The last is fine-tune an LLM on a specific data set to improve its performance on a relevant benchmark. Of course, if you are not good at research, you are not interested in research, you can disseminate technical insights or your understanding through blog on Substack and Medium. That is good because employers look at that, and that would actually improve your employment chances. Now we come to the last portion of the talk on AI governance. This portion of the talk is particularly for those who are thinking of switching into areas which are not very technical, though there is technical AI governance too, which is basically same as alignment. So AI governance lies at the intersection of policy and governance and artificial intelligence. As artificial intelligence is growing in around the world, we need regulations, policies, and proper governance. Because without that, you can have rogue actors who can build LLMs which can harm people. For example, cyber hacking, cyber crime is going to increase, and all those things. So we need policy which should regulate what types of people should get access to GPUs and things like that. So the reason is, why should we govern AI? One of the reasons is that lavender, gospel, and drones are already being used in the wars like Gaza war and Ukraine war. So lavender is used in the Gaza war. It's an AI program which is automating the identification of people which Israel is identifying for killing. So there are many other softwares too. And obviously, drones are also there. And that is why AI is basically dual use technology. So the uses can be positive as well as negative. So we have to be careful with all the dual use technology. So nuclear technology is one of the dual use technology, and that is very well governed. So we want such kind of governance in AI too. Cyber crimes have increased. 87% of global organizations faced AI-powered cyber attack in the last year. This is 2025 report, 87%. So which is huge. Now, 2022 survey of AI researchers by AI Impacts found that median respondent gave a 5% chance that advanced AI could cause human extinction. So there is a 5% chance that advanced AI could cause human extinction, which is actually very high. If you talk about human extinction due to nuclear bomb, it is 4 orders of magnitude smaller. So the chance of human extinction due to AGI or ASI is 4 orders of magnitude higher. So we definitely need strong regulation around it. Renowned scientists like Professor Geoff Hinton, Professor Joshua Bengio, Ilya Sutskever, etc., are worried about some form of AI catastrophe. Professor Geoff Hinton has actually suggested that we should build maternal instincts in AI. So if we look in nature, only mother-child relationship is the only relationship where a powerful being is looking after with love towards a smaller being, a weaker being, right? So that kind of relationship does not occur anywhere in nature. So Geoff Hinton thinks that we should build such kind of maternal instincts into AI. So how to hard code maternal instinct into AI? That is one of the solutions that he's suggesting. Now, if you look at AI triad, we have three things: data, compute, and algorithms. So all three are improving over time. So the quality of data which we use to fine tune and train the models is improving. The data sets are becoming larger. The compute is increasing. We have huge computational units, GPUs now, and new data centers are being built all the time. And algorithms are also silently improving. So the question is, we are moving towards AGI or probably ASI, whether we like it or not. And we really do not have the governance structure to sustain that. Our economy can't sustain that, nor can our jobs, and none of that will sustain that. So the question is, we should regulate the data, we should regulate the compute, and we should regulate algorithms. But the regulation should be such that it does not stop innovation. So, for example, there is a chance that AGI might solve the problem of cancer, and therefore you would want AI to make progress so that in cancer research we can solve cancer. But at the same time, you do not want people to build a coronavirus. So how do you regulate that? You make artificial intelligence better at some things, but still you want to regulate it so that it's not used by wrong actors. So the three vectors where you can regulate is data, compute, and algorithms. Now these are all standard resources which are very useful, and all these have been hyperlinked for your use. You can just click that and you will go there. These are some advanced resources. If you want to try ethical jailbreaking LLM, you can find that these websites give an opportunity for trying that. And this is a useful skill, basically red teaming and blue teaming. So you can jailbreak an LLM and blue team it. Now, these are standard fellowships, which are all related to AI, which you can apply for. Again, these are all hyperlinked. And these last four are scholarships and fellowships, which are very general, not linked to AI. But these fellowships are policy-related fellowships related to governance and AI policy. I have a few FAQs which I have included. One is that, yes, vibe coding and normal coding both are important in this domain. So if you are doing just vibe coding, you have to learn normal coding too. You don't really need a master's and PhD to break into NLP, but at the same time, if you want to do proper NLP research, you want to join FANG, etc., you would definitely require a master's. Uh, and how can one launch an NLP career from scratch? Well, basic math, Python, etc., which I have written. You do not need a formal degree in law, governance, or public policy to build a career in AI governance. So even if you are an engineer, you can build a career in AI governance, or you can be from law, governance, public policy. Many people are there. And AI governance is also a budding field in India right now. I will just show you one or two smart job search strategies on LinkedIn. And with that, I will end my talk. So let's go here. The thing is that if you are searching for jobs, let us say I'm searching for a software development job, right? You will go here, right? Software developer jobs. And here you will see date posted. So in date posted, you say past 24 hours. Okay. So now you will see software development jobs which have been posted in past 24 hours. But algorithms suggest that if you apply for jobs which are one day late, you apply one day late for a job, then your chances of getting selected or called for interview are already 4 times lesser. So typically you should apply for jobs within 24 hours or probably even faster. So how do you make it faster? So first priority should be applying for jobs which have been posted here in the last 1 or 2 hours. The answer is just look here, 86400. Instead of 86400, you just write the number of seconds in an hour. So number of seconds in an hour is is 3600. Now you see these jobs which have just been posted. So this job has been posted 3 minutes ago. This job has been posted 25 minutes ago. And you should prioritize these jobs over those jobs which are late. Okay, so those jobs you can even forget because the chances there is already very low. And since the applications here are very low because these jobs have just been posted, you have a very high chance of getting selected because the HR manager, etc., will look at your application first. So that is one thing. Second is on LinkedIn, you can use Boolean search. Hopefully, some of you might be using it. For example, I want to search a job for AI and I want to search it in, say, Pune, let us say, and I want to search for these keywords like we are hiring. This is typically used by HR people. So now you will get very relevant post here. So you can use Boolean search. You can also do and or depending on whatever query you want to do. So that is another thing. Apart from that, you can also check out jobs on x.com. I have hyperlinked it here. X.com jobs from many startups, and wellfound.com has many jobs from many startups. So with that, I will end. Any questions? Thank you very much. One last thing, there I have given hyperlink to my GitHub. If you just go here, you will find everything linked here. So you will find the code that we used. You will find the references which I have just given you, all hyperlinked, and you will also find my slides there. So that's it. I would love to hear from you. If you have any questions, you can also mail me. Thank you very much.
Thank you so much, sir. Actually, we have good number of questions. Could you please share the link with us, like here on chat, so like many people will ask for the link on live also, so I can share it with them.
Right, I'll do that. Yeah. Okay.
Thank you so much, sir. Okay, so can we move to the questions now, sir?
Yes.
So first question, Murugan is asking, I don't have GitHub knowledge.
Yeah, GitHub is not hard to learn. Um, GitHub, you can actually, what you can do is if you want to just learn GitHub, you can learn it using ChatGPT. You can take snapshots of GitHub and give it to ChatGPT, and ChatGPT will tell you what each button does. So literally, that is one way to learn it. Of course, there are many videos on YouTube which can be useful, but you need GitHub knowledge to do well in this domain.
Okay.
GitHub is just a repository. It's just to store data and files.
Okay, actually, this is the question asked by a person like in the starting. On previous slide, how predictions and label measure loss functions. Actually, I think he's asking about like first or second slide because
Okay. So you are, yeah. So that is, I think, the first or second slide.
yes.
So let us say that I am giving some data, and label is calculating. I'm giving some features of the house I want to buy. So there is like the square feet, number of rooms, location, etc., etc. They are the features, and the label is like the price of the house, right? And LLM is predicting what the price of the house will be. So let us say that the price of the house predicted by LLM is five 5 crore, and the label says that the correct price corresponding to that house is actually 2 crores. So the loss is 3 crores. So 5 minus 2 is 3 crores, and that is propagated backward to the weights of the LLM. So the weights of the large language model or neural network in this case are adjusted such that the answer lies close to 2, if not exactly 2. So the same thing happens with each and every example. I think you can watch one or two video lectures on neural network and you will understand this.
Okay. Okay. Another question. Any good reference link for MLOPs?
ML ops, yeah, I mean, I'm not an expert in ML ops, um, but I think I can add a few reference links to my GitHub profile, Git repository, and you can find it there. Right now, I have not added any ML ops links here.
Oh, okay, Hariharan is asking which is best fine tune or RAG based?
This all depends on the application that you have. I skipped this one slide where I've tried to summarize this. So it depends on the application, right? Every so REG has RAG has different benefits and weaknesses, and fine tuning has different benefits and weaknesses. So if you have a lot of compute, you do not have any problem with compute, and you have a lot of data, then you can do fine tuning. But if the data is less and if the compute is less, and your main focus is on reducing hallucinations, that is improving the factual answers given by the LLMs. For example, companies have chatbots, right? The chatbot interface, Amazon has its own chatbot, and that chatbot probably has RAG access to it. Although it might also be fine-tuned, but it will also have RAG access so that the answer about company policies or return policy for an Amazon article is very exact. If it is 7 to 10 days, it is going to exactly say 7 to 10 days. If it by mistake hallucinates 20 days, then everything is going to go wrong. So RAG is mostly used where the factuality is very important. So typically, you should build a model using RAG as well as fine tuning. That would be like an ACE model.
Okay. Okay. Another question. Which is best for research paper based fine tuning for LLM? Which method is best, fine tuning or RAG?
I think the question is little ill-framed. The The question being asked is probably that whether I should build a RAG using research papers or whether I should fine tune a model on research papers. Probably that is the question. Again, it depends on what you are interested in. I would say fine tuning would be more appropriate because you would want the model to really learn the research papers. So learning the research papers only happens in fine tuning. In RAG, the model is not really learning it. It is just given an external book, which it can refer anytime. So I think if the question I understood correctly, then fine tuning would be more appropriate. Then the LLM will be able to understand research better.
Okay. Another question: how do you see AI impacting jobs in the next 5, 10 years, especially for freshers?
I think we are already seeing the impact. The impact is that freshers are finding it very hard to get a job, and the skill set required of freshers to get a job is actually increasing every year. So my understanding is that you should upskill yourself all the time. There is no other way. And that is one of the reasons I wanted to show you the fundamental research papers so that I encourage you to do some research, probably publish a few research papers, because I have seen that even BTech students now are actually coming out with 3 or 4 research papers in duration of 4 years of studies. So the competition is very high, as well as companies like TCS and all these companies have fired so many people. So uh, jobs are definitely getting impacted, especially for freshers. So your skill set has to be as strong as possible. Put your best foot forward.
Okay. Another question, Arnab is asking, what is the preparation time we should keep to get into this field?
So if you are completely starting from scratch, let me say you have not studied NLP, let me say probably even not much of neural network, you might take an year to complete. I mean, it depends on the speed. It's very hard to answer because if you are already doing a job, you might not have much time, so it might take long. But if you are doing it full time, then probably you will do one course on, say, neural network, then you will do another course on, say, NLP, then one course on, say, large language models, things like that. So maybe 3 or 4 courses, and then you will start doing courses from deeplearning.ai, which teach new tools and techniques like RAG and whatnot. So maybe 4 or 5 courses are sufficient to get a hang of it. Also, you'll need to practice a lot, build your own projects, do research if possible. Yeah, there's no hard and fast answer to this.
Okay. Another question, what are the most important skills a fresher should focus on to start a career in NLP?
I think the most important skill is probably mathematics. So the basics like linear algebra, statistics, these are probably more important than even neural network. So you will understand neural network only because the neural network today, the large language models are actually doing a lot of matrix multiplications, which is linear algebra essentially. So you need to understand what is going on behind the hood. So for that, you need the basically linear algebra and statistics.
Okay. Another question is related to this only. How important is a strong math or coding background for starting in AI NLP?
I think math background is much more important than coding background. Um, so I know of many people who have switched from different areas, including me. So I didn't have much of a coding background, and neither am I a very good coder at the moment. But still, I think mathematical foundation is much more important to do to contribute in this area.
Oh, okay. Another question. Any advice for seniors who have already spent 20, 25 years in the in IT industry but not in development? How to change tracks now?
I am assuming that again, this is in context of AI development. So I think changing tracks is easier if you switch to a first. Then from startup, you can switch to a multinational company later on. So startups are much more tolerant of people who are making a career shift. I would suggest they should look at startups. For example, I spoke about X jobs or well found. You can search those websites. They have a lot of startup jobs.
Okay. Is LLM is a extension of NLP?
So natural language processing is a domain. And to do language processing, you have different kinds of computer models. One of the models which does natural language processing very well is LLM. So apart from LLM, you have other models like BERT model. You can have other models also like RNNs, which is also based on neural networks. So you can have many types of models which all do NLP. So NLP is the task, which is natural language processing. It's the task.
Okay. Another question. How to give the weight metric to the query key and value? Is it any number? How to know?
Yes. So while you are training the transformer, let us just go there for once. So while you are training the transformer, you will train the weight matrices for query key and value. So these are already fixed. WQ, WV, and WK are already fixed. So you don't have to do anything. While inferencing, that is while generating the prompt, what you are trying to do is just multiply it. So these matrices are already trained during the training of the large language model or the transformer.
Okay. Uh, Another question. Does import embedding uses embedding system programming?
So, I mean, you are probably talking about the code. So, with respect to the code, I think there are many ways of doing same RAG. So there is no one way. You can find 5, 10 times, 10 ways of doing RAG. So I'm not sure if I understand the question perfectly, but yeah. So I think there are many more ways. So even if you want to pursue your own way, that is fine.
Okay. Another question. What does masking mean here?
Okay. So masking means that you are not showing the decoder the future tokens. So the can only see the, it cannot see battery, fired, or shells. It cannot see it. Just it's not being shown at all. So I gave the example of a student who is in the maths class and he has to answer the question the teacher has given based on only the knowledge teacher has given in his lecture. The student does not have access to the book which shows the future. So the next chapter the student cannot access. So that is called masking. So this is the student has been masked from seeing rest of the knowledge. So similarly, the language model is actually masked from looking at the future tokens. And that is very important because unless and until future tokens are masked, it will never be an auto-regressive model. It will never be a next token generator, a good next token generator.
Okay. Another question. I have fine-tuned using Mistral 7B for SEO and product marketing. The name of the fine-tuned model is Sepro LM. Does anyone have interest to check it out? So yeah, we'll
Yeah,
check. Okay, so Hariharan is asking why everyone is hyping AI instead of getting into it. I have met lot of people who tells I am studying AI is only for money, but AI is all about passion, right?
yes. I mean, working in AI is in some sense a privilege because this is the most transformational technology of our lifetime. if AGI or ASI is developed, it will solve problems from cancer to environmental issues to climate change. You name it, and it will solve it. At least that is the hope. So this is going to be the most transformational technology we can ever work on, or humans have ever created. So that is why AI is being hyped. And the hype is not wrong in the sense, because the promise of AI is huge. Although the large language models have not yet attained that promise, but the promise is huge.
Okay. Another question. What is AGI and ASI?
So AGI means artificial general intelligence, and ASI means artificial super intelligence. So general intelligence is when an AI model has similar capabilities as a human. So it has the same intelligence as a human. So some capabilities already LLMs have, but it is not, at least at the moment, at AGI level. So soon enough, maybe by GPT-6, GPT-7, GPT-8, it might be at AGI level, which is at the same intelligence level as humans. ASI is actually even beyond that, this super intelligence. So what happens is the AI model is so intelligent that it is going to improve itself infinitely. So it is just going to improve itself on and on and on. So that is super intelligence. That is super intelligence explosion. So this is like an infinite ladder that will be opened up once we achieve that.
Okay. Another question. What are the emerging trends in NLP that freshers should be aware of?
I mean, the most emerging trend is always, um, at the moment, obviously, large language models and transformers. And that is why I think Shine.com has actually arranged this talk. So, yeah,
Okay.
I mean, there are also other models which are coming up, like JEPA. If you are interested, you can check that out. It is not that big at the moment, but maybe it will be important in times to come.
Okay. Hariharan is asking, I have predicted the future of AI evolution, maybe GSI, generative superintelligence. What's your thought about it?
What's my thought about artificial superintelligence?
Uh, n- he's saying, I have predicted the future of AI evolution, maybe GSI. What's your thought about it?
I have no thoughts about it. I am not sure what is what he's trying to ask.
Actually, he is
So,
trying to ask that GSI, generative super intelligence, is a future of AI. So he
okay,
wants to
okay,
know what's
that's a
your thought.
terminology he has coined, and I congratulate him for that. But I have no opinion on that.
Okay, so another question is, sir, can you give a similar roadmap for learning AI agents and agentic AI?
Right, right. I mean, the next step after doing fine tuning and RAG should be agentic AI, and there are many courses, many lectures, and a lot of material on that. What I can do is I will put that material, compile that, and put it in references of my GitHub repo, the link of which has been given to you. I will keep updating the GitHub repo with new papers, new fellowships, and new ideas like agentic AI. So I will do that.
Okay. Another question, does RAG is line similar to SQL to RDBMS?
What, can you repeat the question, please?
Does RAG is line similar to SQL to RDBMS?
So relational databases are different from vector database. Vector databases are used for semantic searches. So therefore, this is similar in the sense they are databases, yes, but the point is here the search is semantic. So you can use natural language to do the search. So the vector embeddings are done for the chunk of the data, and that is how the RAG is built. Yeah, so there are similarities, but this is vector database and that's a relational database. This is useful for semantic search, large language models.
Another question, how the database or data storage of LLM will look like?
So LLM does not really have data storage. LLM stores all the information or the data in form of its weights. So the question is very good one, that how will it look like? And that is what mechanistic interpretability is doing. That's an area of study where people look at how these weights or what weights store which information. So where is the information, say, capital of France is Paris stored, or say capital of India is Delhi stored. So this structure, how is that stored in the whole neural network, is actually being done by mechanistic interpretability. But they are doing at the moment with mostly toy models, because looking at a very big model like uh, 200 billion parameters, etc., is actually very, very hard and intractable problem. So that's an active area of research, and the question is good, but we don't really have a particular answer. They are stored somewhere in the weights. So hard to answer how they are stored exactly.
Okay, so we are done with the questions. Oh, we have one more question left. Do LLMs store the inferences also for future use?
Okay, so let us say I ask an LLM, what is the capital of India? And the LLM will respond, the capital of India is New Delhi. Now, next I ask some other question like, what is the capital of France? So in the context window, it already has the first question and its answer. So these answers are there, but are you asking whether it will store it for some future reference? By storing, an LLM will have to update its weights. So LLM is not updating its weights while you are doing inferencing. So I might ask 20 different questions. ChatGPT is, sorry, OpenAI is probably storing that somewhere in some cache or something. That's a different story. But LLM is not storing those questions and answers. So the inference results are not being stored by the LLM. Only when you are fine tuning a model or updating the weights, the results can be stored. Otherwise, unless you are updating the weights, it's not possible to store something in a LLM. The LLMs, especially proprietary LLMs, are all frozen weight LLMs. So their weights are all frozen and we cannot look behind the hood. So we don't know the weights are, and we don't know how to fine tune it. So mostly they are not even available for fine tuning.
Okay, so we are done with all the question. But before ending this session, like any piece of advice for freshers you would like to give?
Yeah, I think just having, just studying the right basics is not sufficient right now. You will have to build relevant projects. So the projects that one sees in CV nowadays are random, fine tune, some LLM or some RAG, etc. And that's not going to work. You need to have relevant projects which really solve a real life problem. Or you can have research papers. You can write research papers in collaboration with people. Apart from that, you should also, as I said, do job search smartly. Search for those jobs which have just been posted, like 1 hour ago, 2 hour ago, apply for them first. And obviously the basics like for this domain, linear algebra, statistics, probability, and then Python coding, neural network, etc., are all very important. So there is no one shortcut to success in this domain. You'll have to do the whole compass. You'll have to do everything there is.
Thank you so much, sir, for delivering such a clear and engaging session. We truly appreciate you taking time to share your knowledge with us. And A big thank to everyone who have joined us today. We hope you found the session useful and informative. If you would like to revisit the session or share it with others, the recordings are also available on our LinkedIn page and YouTube channel. So until then, take care, stay curious, and keep learning. See you all next time. Thank you so much, sir, once again.
Thank you.
Thank you. Bye bye.